All right, so this is 4.7. This is justifying congruence. And after this lesson, you should be able to describe a sequence that will map a pre-image onto an image and thereby show congruence. And describe a sequence of transformations that map one figure onto another congruent figure. That's effectively saying the same thing twice. So let's get right to our first example. Right, you should be able to understand that when you have two, and I mean, in the past, we've been just giving you, one shape and or multiple of the same shapes and saying, hey, when you rotate this or flick that, or you apply these rotations, what does the shape look like? Or this is the before shape and this is the after shape. What were the transformations? Well, now we're going to say, hey, these are the before and after shapes. What do you need to do to map these shapes on top of each other to prove that they are congruent? And remember that as long as they are rigid transformations, the transformations will be congruent. All right, so here's our first set: quadrilateral KFTD and quadrilateral KSRW are shown on a coordinate plane. Yes, they are. Describe a sequence of transformations that will map the K1 to the X1. That's the blue and the yellow. So this is our blue one. Our blue one here. And our yellow one. Our yellow one's here. I'll cover up the coordinates. Our yellow one's here. Okay, well, so go ahead and take a look at that. There's multiple different ways you can do it. Push pause button and see what you can come up with. You can use table method, patty paper, copy and paste on Word or a Paint, and then flip and flop it. And see what you can figure out, and I'll be back. Okay, I'm back. So what did you figure out? Well, this is the way I did it. I looked at it and I said, well, in order for me to be able to mirror or to place this image on top of this image, it needs to be reoriented. And in order to reorient this image, it needs to be pretty much facing the other way. This pointy end needs to be facing the same way as that pointy end, and this needs to be facing up. So this needs to be reflected. It needs to be reflected across the x-axis or the y-axis. So the first thing I'm going to do is make this a table. Make a table. My blue one, and a reflection. I know the coordinate, the coordinate comparison for reflection across the y-axis is going to be x, x, x. Well, first I need to be x, y. I need to copy those coordinates down, I guess. Up the cart before the horse here. Go x, f, t, d, p, d. And let me copy those down here. I got -2, 9, f is 3 and 4, p is 1 and 2, and 2, and then d is -3 and 5. Separate with a line, and then I'm going to use orange for my next set of x and y coordinates that are going to be derived from the blue x and y coordinates. They're going to get reflected, and the x and y coordinates don't change when they're reflected, but the x is going to ride the x and not get changed, but the y is going to shift signs. as it rides the x coordinate for each point. So the x is going to stay -2, but it's going to shift to -9. And all my x's are going to stay the same. 3, 1, -3. And all my y's are going to shift signs. -4, -2, -5. All right, so now that's going to put me in the right orientation. I'll go ahead and just kind of log or plot that to -2. That's -9. It's like way down here, way down here. That is my x prime. 3 and -4. That's like right here. My f prime. And I got t is 1, -2. That's my t prime. Now I have -3. -3 is here. -5 is like right here. What was x again? X is negative. That's not the wrong spot. Oh yeah, that's like that one. Okay, that's x prime. Okay, so now this is a what's that? That was a d dots here. This one. This one. This one. This one. Okay, there is my. That looks a little short, doesn't it? Double check that. My t is 1. Maybe it's a little shorter one. And -2. Okay. And f is 3. That's a problem. It's not on 3. F's on 3. -4. It looked a little off. Now it looks a little better. Okay. Okay, and this is my f. All right, so now f. Now I have all I got left to do is slide it over and up a few. So I think I'm just gonna count this, coordinate count this. So I'm just gonna go red. Now I'm gonna use I think my f to coordinate. Maybe not my f. Here's my t. I got 1, 2, 3, 4, 5. My delta x is 5. And then my delta y is 2. 2 delta y is 2. All right, so now I have delta y is 2, delta x is 2, so now I can write my expression. I got it. X comma y equals x plus 5 y plus 2. Now I got my blue one. X comma y drawn from x -2. All right, so that is how you do the first one. And you could see that, I'll plot that with the red one. X is 1, 2, 3, 4, 5, 1, 2. And that was F. That was F. X is goes to R. 1, 2, 3, 4, 5. 1, 2. It was almost like it was 3. That's probably an error somewhere or something. 1, 2, 3, 4, 5. And then like 1, 2, 3, 4, 5. There was an error on that one too somewhere. But by 1. But and then no, that's not true. 1, 2, 1, 2, 3, 4, 5, and then 1, 2. That went up 3. I must have had an error in there too somewhere. But that's the basic idea. And that will probably had an error up in here when I translated it, or maybe when I counted it. But that is how you put it together like that. I wonder what happens if I do delta 5. Delta 5. Oh wow. Plus 5 and plus 2. 5 plus 2 to each one of these. X and Y. All right, so I do negative 3. No, it's not. It's going to be 3. It's going to be 3, 8, 6, and 2. And this is going to be negative 7, negative 2, 0, and negative 3. See if I have a point in all these places here. Okay. 6 and 0 is K, which lines up with T. That one's check. I have an 8 and negative 2, which lines up with F, which lines up with S. That's check. 3 and negative 7. That's R, which lines up with X. That's check. 2 and negative 3, which is W. Okay, that's your check. All right, well, so all those lined up. So all of them were right. I just guess I miscounted on the grid or something. So I guess the table is more effective there than the grid is. So anyway, moving on to the next example. Oh, hey, look at that. The next example shows you that the table didn't line up with the actual things. He said, hey, what were the points that lined up with all the different things? We kind of already identified that. If you go back and look, you can see that my points didn't line up with the original points that were sequenced, because this is an X. Negative 3 and 7 is R. So negative 3 and 7 lined up with X. So my R and X lined up together. Yep. So you can see that. Shrink this so you can see it. Negative 3 and 7. Negative 3. Negative 3 here, and 7 lined up with X. You can see that negative 8 and 8 negative 2. 8 negative 2 is S. And S lined up with F. You can see that 6 and 0. 6 and 0 is K. And then lined up with T. And the last is W and D. So another reason why the table method is superior. A lot easier to pick data off it like that. Okay, so here's another Another one more. Let's one more example. We have these two coordinates. Oh, and it might ask like, hey, why were those quadrilaterals congruent? Well, it might be because, hey, how'd you line up the vertexes, right? All the vertexes, you just have to say, hey, the vertex is, you know, each vertex mapped on their specific other, matched vertex. And you can say that. Let me go ahead and back up for a second. Since we have this table here, I have this specific table here. Copy and paste something from the book here. Say because the vertex K mapped with the vertex T, and S mapped with F, and R mapped with V, W mapped with D, the definition of congruence in terms of rigid motion justifies that ASRW is congruent to TFXD. So the order in which you order your letters matters. That's all I wanted to put out. It wouldn't be KSRW is not congruent to KFTD. It's congruent to TFXD, right? So just that's a point. It matters, right? Because the definition of congruence in terms of rigid motions is two figures are congruent if and only if there exists one or more rigid motions which will map one figure onto the other. Okay, so just remember that. All right, so we have one set of quadrilaterals. These two quadrilaterals, and use algebraic expressions that will map on these things. Right, so one little note here: when we're writing at the very end, we're going to use the algebraic expression, so you're going to definitely need to use the tidbits here. That just made it worse. All right, so when we're using rigid motions to map one figure onto the other, be sure to match the corresponding vertices before stating the congruence, right? That's at the very end there. So we'll use a table, we'll use two tables there, or we'll just combine the two tables so that we can identify what the order of the vertices should be. The vertices are the letters, what they're named after. Okay, so let's figure out how. You guys go ahead and pause the video real quick and see if you can figure out what what you can how you can transform these two be. See, this is the pre-image, and this one's the after image. See if you can figure that out. All right, so here we go. All right, so the first thing that I note is that they're different orientations. Okay, so if I need to reorient this one way. If I reflect it, it's still going to be pointing upward. The original one, we'll call this one blue. Call this one blue. Call this one red. Right, blue is still going to be facing upward when it needs to be facing. We'll say the nose of it needs to be facing left. Okay, so what's going to make this thing's nose face left? Well, if I rotate it this way, the nose is going to face that way. But if I rotate it this way, the nose 90 degrees, the nose will be facing that way. So that'll get me in the position that I needed to be facing. I could rotate it 270 degrees that way. That'd be fine. But that's the same as rotating it 90 degrees that way. So I'm going to rotate this guy 90 degrees that way. So what is the algebraic expression for a 90 degrees counterclockwise rotation? Well, remember x comma y. That's every way that we start a transformation, and then rotations of 90 degrees or 270. Anything that's not 180. Whoops, that is not 180. Starts by swapping the x and y coordinates. To x and y coordinates, x and y, and counterclockwise rotations, put a negative sign in front of the y's because they swapped the y's. The sign of the y's. All right, so we're going to use this coordinate comparison for to get our intermediate transformation, and then we're going to do a translation to move it whatever number we need to move it. So let's do that with the table again. All right, so my x and y, x comma y, make it a little bit bigger for some space. X and y, and I'm going to pull B, G, L, W, B, G, L, W, and I'm going to totally disregard H, Y, C, T because I know it's not going to be the same. I'm going to have to reorder it. B is -9, -1. G is -6, -5. L is -2, -2, -2, and -2. And W is -4 and -4. -4, -4. Okay. And then I'll go green with intermediate purple. Okay. And so I'm going to have my comparison coordinates. And then my final, this is my new coordinate, x comma y. And that's going to be pulled from the negative y's of my old pair and the regular x's from my new pair. So my negative y's are going to be 9, 6, 2, 4. And then my negative and my y's are going to be -1, -5, -2, and -4. Okay. So let's see now. I have to plot this because I don't know where I'm supposed to, what one's supposed to go to which one. It looks like you got 7 and negative. Yeah, I don't know which one's supposed to go to which one, so I really do have to plot this. -1, -1. That one goes there. 9, -1, 6, -5, 6, -5. Either, like I said, I don't know these ones yet. I don't know what they're supposed to go to yet. 2 and -2. And then 4 and -4. There you go. Doesn't look like that's the right image, does it? Well, let's double check. 9, -1. Check 6 and 6 and -5. Yep. 2 and -2. 4 and -4. Okay, where did I make an error? Okay, this is supposed to be -6. Nope, that's supposed to be 6. Okay. I transfer all my numbers right. 6 and -5. Nope, I did not transfer that right. That is 6 and 5. So this is 6 and 5. This should be 6 and 5. 6 and 5. 6 and 5. That looks better, I think. Let me double check here. Okay. Still looks a little funny. Really funny. Okay, let me double check my copy of 9 and -1. -6 and 5. -2 and -2. -4 and -4. Okay, that's all right. So I flopped them. -9, 1. That's right. -6, 5. -2, 2. -4 and 4. I plot them right. 9 and -1. 6 and 5. 2, -2. 4, 4, and -4. Okay, let's see what happens if I connect the dots. Maybe I chose the wrong one. Yeah, I did choose the wrong one. It's just 180 out. All right, I'm gonna pause this just for a second. All right, so I misjudged my rotation. I think that was more of a half of a rotation to get it pointed the right way. But am I lost? No, I'm not lost. I can still. I'm about 180 degrees out. So I think if I reflect this across the y-axis, I might be pretty close to where I need to be. So let's take a look to see what happens if I reflect it across the the x-axis. So a reflection is going to be, I'll use orange. So reflection for the new, no, that's not what I need. I need pencil for reflection for the new, I change that color for the new x and y axis, the new xy points. XY points is going to be pulled from the purple ones. They're going to be still XY, but across the x-axis, the y values flop. So that's going to be negative the y value, or the opposite of the y values. So let's get that to work. Okay, so the x values stay the same. The x values stay the same. And the y values are going to change in sign. So let's do that. So we got 9 and 1 now. It'll be 9 and 1. 6 and -5. 6 and -5. And we're going to have 2 and 2. 2 and 2. And we're going to have 4 and 4. And let's connect those. See if we're close. That doesn't look right. All right, so I backtracked to where I made my mistake. I didn't actually apply the uh, coordinates right. I don't know what I was doing, maybe because it's 10 o'clock on a Sunday night, but I didn't actually swap the X and the Y when I did this. All right, so I didn't actually draw the the like the Y's from the X coordinate and the Y and the X's from the Y coordinate. I didn't actually do the thing I was supposed to do. So here we go again. I'm gonna do it right this time. Okay, so the X's are drawn from the negative Y coordinate. So this is 1, -5, 2, and 4, because the X is drawn from the opposite of Y, and then the Y is just drawn from the X's. So this is -9, 6, -6, -2, and -4, -4. So let's plot those now. 1 and -1 and -9. It's way different. 1 and -9. Okay, and -5, -6, -5, -6, -5, -6, oh, -5, -5, -5, -6. That's right here. 2 and -2, 2 and -2. And then we have 4 and -4. That seems better, more correct. All right, so let me go ahead and link that together. That seems like I was wondering why it looked way wrong. I didn't do the thing right. That looks better. All right, so now we have to translate some points over. And to do this, I'm just gonna, I could 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. X is 6. So X equals 6. And 2, 4, 5, 6. So double check. 1, 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4. Oh, what's going on here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh no. 1, 2, 3, 4, 5, 6. I bet this one's over the scooch too far. I bet that's supposed to be. No, that's there, right? Okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I bet X is supposed to be delta 6. X equals delta 6. But I plot something wrong. Let's see. 1, -9. -5, -6. 2, -2. 4, -4. No, I didn't. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I think it's 6. Maybe I'm just counting. All right, so delta 6. And how many need I go up? 1, 2, 3, 4, 5, 6, 7. And Y equals 7. Equals 7. All right, so I think my X equals delta 6 and Y equals delta 7. All right, so the two that I am going to need to use here are X comma Y is going to be drawn from negative X comma negative y, and then x comma y is going to be drawn from x plus 6 comma y plus 7. And if you can see from here, that is what it's calling for. Hey, honey. All right, so finally, we have to just match the points here. So grab them here, and then looks like that T and G match. So that's T. This is T with G, and H with L, H with L, W with, oh, wait a minute. Yeah, W with Y, and then B with C. B with C. So that means that our triangle, our quadrilateral, that was original B, G, L, W, L, W is congruent to BGLW. It's congruent to C, T, H, Y. Okay, and you have a give a table like this with statement. Looks like this. So when you're at the table, then you'd fill in this here with, before you state your complete the congruent statement. Right. So remember, when you're using rigid motions to map one figure on the other, always be sure that the corresponding vertices match, or the points. Points vertices are the same thing there. Okay, so that is pretty much it. So if you have any other major questions, please let me know. There's homework on here too to help exercise any other thing that you have questions on. Thanks. Have a great day. And remember to learn from my mistakes so you don't have to learn from yours.